Hello and welcome to Lesson 4 of 20 in the Ursa Campus Breakdown course on Introductory Statistics and Probability. This is Module 1, Introduction to Statistics, Part 4, Descriptive Statistics, Measures of Dispersion. Let's get started. In the previous lesson, we looked at measures of central tendency, which give us a sense of what the average or typical values are for a data set. Measures of dispersion, on the other hand, tell us about how much data values are spread out around those central values. In this lesson, we're going to be looking at the following different measures of dispersion: range, mean absolute deviation, variance and standard deviation, and then we'll look at dimensionless measures of dispersion, the mean relative absolute deviation and the coefficient of variation. Of note, each of the measures of dispersion that we'll be looking at in this lesson can only be applied to numerical ordered data. So that means that all qualitative data, as well as quantitative data that's nominal, cannot have any of these measures of dispersion. The first measure of dispersion we'll look at is the range, which is the overall dispersion of a data set. The range of a data set is simply the difference between the minimum and maximum value. So range equals maximum value minus minimum value. In example 1, we have the following data set showing the number of cars owned by each household on a street with 12 households. If we put this data set into increasing order, we can see that the minimum value is 0 and the maximum value is 4. So therefore the range equals 4 minus 0, which equals 4 cars. In example 2, we have a set of integers with a minimum value of -5 and a maximum value of 6. So the range there is 6 minus -5, which equals 6 plus 5, which equals 11. So whereas the range is only influenced by the extreme, i.e. minimum and maximum values in a data set, the remaining measures of dispersion we'll be looking at take all values in the data set into account. The simplest of these measures is what's called the mean absolute deviation, or MAD for short, which is the weighted average of the absolute differences between each data set value and the mean. So the MAD equals the sum of the absolute deviations for all values in the data set divided by the number of values in the data set. And mathematically, that formula becomes, for a population, the MAD equals the sum of the absolute values of each x minus mu divided by big N. And for a sample, the MAD equals the sum of the absolute values of each x minus x bar divided by little n. Now, for a particular data set, these are basically equivalent equations, so you'll get the same value for the MAD whether you treat a data set as a population or as a sample. The purpose of the absolute value brackets in the calculation of the mean absolute deviation is to ensure that each difference is expressed as a positive value. Now this is because in any data set where all the values aren't identical, you're going to have the mean being somewhere in the middle of the data, and some values in the data set will be below the mean, and that would give a negative deviation, and some values will be above the mean, and that will give a positive deviation. Now mathematically, if you add up all of the deviations, so if we didn't use the absolute value sign, so if it looked like the way it looks on this slide here, where we just sum up the differences between each value and the mean, they would actually all cancel each other out, and you would end up with 0 on top in the numerator. And regardless of what the size of the data set was, regardless of what n was, it would always be 0 divided by n, which is 0. So without the absolute value sign, the mean absolute deviation would always equal 0 regardless of the data set, and we don't want that. We want the mean absolute deviation to mean something. So for that reason, we use absolute values. And what that does, in essence, is it combines all the positive and negative deviations together in the same positive direction. In example 3, we're given a data set which represents the numbers of seeds out of 10 sowed which germinate in 6 successive trials. So we see 6 numbers here, and each of the numbers represents how many of the 10 seeds sowed in that sowing germinate. So the first step is to calculate the mean. So we add up all of the values, and there's 6 of them. So we add the numbers up, which is 24, and we divide by 6. So we get a mean of 4 seeds. And now we can calculate the MAD. So what we do is we add up for each of the individual values. We take the difference between that value and the mean, which we've just calculated to be 4, and we take the absolute value of each of those differences. We add them up and divide by 6. So you can see on the slide that we end up with some of the values in the absolute value signs are negative and some of the values are positive, but because we're taking the absolute value of each number, all the negative values end up being positive. So the sums of the absolute values is 20, and we divide that by 6. So we get an MAD equal to 20 over 6, which equals 10/3. Now this answer can be represented a few different ways. In reduced fraction form as a what they call an improper fraction, and we get 10 over 3, where the numerator is larger than the bottom, so that's 10 over 3. We can convert that to a mixed fraction, which is 3 1/3, so that's another way we can represent the answer. And because 1/3 is a repeating decimal, we end up with the final answer of 3.3 repeated. So 3 point, and then we have the dot over the 3, so 3.3 repeated seeds. And this means that on average, the number of germinating seeds in a sowing deviates from the mean number of germinating seeds by 3 1/3, or 3.3 repeated seeds. Now, the mean absolute deviation gives us a very straightforward and easy to understand measure of dispersion within a data set. It's simply the average of the absolute values of the deviations, and that's, relatively speaking, straightforward to understand. There are some mathematical limitations to the mean absolute deviation, however, the details of which are beyond the scope of this course. But what's important for us here in this course to know is that the MAD has these mathematical limitations which limit the usefulness, the utility of the MAD as a statistical measure. Mathematicians prefer to use something called the variance. Now, the variance is a measure of squared dispersion. So the way the variance gets around the problem of how some deviations are positive and some are negative, and they would just cancel each other out if they were added, as we talked about before with the MAD. What the variance does is it squares the deviations, and of course if you square something, if it's negative it'll be positive. So by squaring the deviations, you're adding a bunch of positive things, which similarly gets around the problem of in the way that the mean absolute deviation does. So with the variance, there's actually two slightly different formulas depending on whether you're looking at a population or a sample. So if you're looking at a population, the population variance, the symbol for that is what we call sigma squared, and the sigma is that's a Greek letter. It's the lowercase version of sigma. So sigma squared is calculated as the sum of the squares of each value minus the mean. So you take the value minus the mean and you square it, and you add that up for each value, and you divide by the population size, big N. Now, With a sample, the variance is calculated similarly in the sense that we do add up the deviations between each value and the sample mean, which is x bar. So for each value, you take the difference between x and x bar, you square it, and you add those up, and that's your numerator. But the denominator, instead of dividing by the sample size little n, you actually divide by the sample size minus 1, or little n minus 1. And the mathematical reasons for that are again, somewhat beyond the scope of the course, but what is relevant to know for this course is that the reason we divide by n minus 1 instead of n is that by doing this, the value of the sample variance, which we call s squared, is an unbiased estimate for the population variance. So we can use s squared for a sample to give us an unbiased estimate for the population variance, sigma squared. In example 4, we look at the previous data set, where we calculated the mean to be 4. And if this data set is considered to be a population, we calculate the population variance using the formula discussed previously. So what we do, we can see here, is we are going to add up for each value we're going to take the square of the difference between the value and the mean. So you can see, and then we divide it by the population size, which is 6. So as you can see on the slide, we have the sum of the squares of those differences divided by 6. And similarly to with the MAD, all of the negative deviations, because we square them, will become positive. So we end up adding up a bunch of positive numbers. And so the sums of the squares of the deviations is 80. And so sigma squared equals 80 over 6, which reduces to 40 over 3, or 13 1/3, or 13.3 repeated seeds squared. In example 5, we again look at the same data set, but this time we treat it as if it was a sample from a larger population instead of a population itself. So this time we're going to calculate the sample variance using the same set of numbers. And so we use the formula for s squared, which, as we discussed previously, the numerator ends up being the same. We basically take the sum of the squares of the deviations, but this time we'll divide by little n minus 1. And so we end up with that same numerator value of 80, but this time instead of dividing by 6, we divide by 5. So we end up with a value of s squared equaling 16 seeds squared. Now, note that the value of s squared will always be somewhat larger than the value for sigma squared if we're basing it on the same set of values. So in this particular example, we got s squared equaling 16 versus sigma squared equaling 13.3 repeated. And the reason, of course, for this is just purely mathematical, is because the same sum of squared deviations is being divided by a smaller number, n minus 1, in the case of the sample variance, compared with dividing by n in the case of the population variance. Now, you might have noticed in the last two slides that one drawback to using the variance as a measure of variation is that the resulting units are not the same as those of the data set, but rather they're the square of these units. So what we saw in the last couple of slides was that we were getting either population or sample variances in units of seeds squared, which really doesn't have any relevance to this particular problem, versus the actual units of interest, which is number of seeds. So the solution to this problem is to take the square root of the variance, and this is how the population and sample standard deviations are calculated. So the formulas on this slide show us that that the population standard deviation, which is equal to sigma, is simply equal to the square root of the sum of the squares of the deviations, x minus mu, divided by the population size, big N. While the sample standard deviation, which equals S, is equal to the square root of the sum of the squares of the deviations, x minus x bar, divided by the sample size minus 1, little n minus 1. In example 6, we go back to the previous example, the data set, and we consider it as a population, and we calculate the population standard deviation, sigma, by taking the square root of sigma squared, the population variance. So we end up with the square root of 40 over 3, or the square root of 13.3 repeated, seeds squared. And we get an answer rounded to 1 decimal place of 3.7 seeds. And note that the answer now has the units seeds, not seed squared, but the units seeds, which is the same as the units in the data set, the original base values from the data set. Now, you'll see in brackets after the answer of 3.7, we see also the answer shown rounded to 3 decimal places, which is 3.651 seeds, which it says here is for any further calculations. Now, we need to discuss here a couple of notes regarding how we deal with numbers that are not exact and need to be rounded. And so we're going to discuss some rules and general rules of thumb that apply not just to this particular example, but the entire course, and how we'll proceed in situations where we have numbers that are not exact and need to be rounded. So the first note here is that the use of the wavy equal sign that you see above in the slide, it signifies that the answer is not exact, but rather has been rounded from an infinite decimal to a fixed number of decimal places. And the notation we'll use for decimal places is dp. When rounding is necessary, the following general rule of thumb is used for the purposes of precision and accuracy. Now, firstly, for precision, final answers should be taken to 1 more decimal place than the base data value. So in this particular example, the base data values in the data set have no decimal place. They're whole numbers, so they have 0 decimal places. So what we do here is we round final answers to 1 more decimal place than 0, which means 1 decimal place. So that is why we've rounded the answer here to 1 decimal place, and it is 3.7 seeds. Now, if a rounded number is going to be used as an intermediate value for any further calculations, in other words, if you need to use that value again later on to calculate something else, then at least 2 extra decimal places should be carried. And in this course, we'll generally use 2 extra decimal places. So since we're rounding the final answer for sigma to 1 decimal place, if we were going to use that value later on for any further calculation, we would round to 1 plus 2, which is 3 decimal places, which would be 3.651 seeds. In example 7, we work with the same data set again, but this time we treat the data set as a sample, and now we calculate the sample standard deviation S, which is the square root, this time, of the sample variance, S squared. And so we end up with the square root of 80 over 5, which is the square root of 16 seeds squared, which equals 4 seeds. Now note, in this case, the answer is exact. It's exactly 4, because it so happens that the value for S squared happens to be a perfect square of 16. Now this usually won't be the case, and in most instances, just due to random chance, rounding will be required, because the number that we'll be taking the square root of won't be a perfect square, as was the case in the preceding calculation of sigma. Now we turn our attention to dimensionless measures of dispersion. Both the mean absolute deviation, MAD, and standard deviation, whether it's sigma or S, provide measures of dispersion in equivalent units to the dataset values, which is a good thing because it makes it straightforward to understand the meaning of those measures. However, this does pose a problem if we want to compare the relative dispersion between two or more data sets particularly that are using different units of measurement. This is because the magnitudes of these measures are influenced by the choice of units. In other words, the larger the numbers, the larger the values for the measures of dispersion. In example 8, we consider the following two sets of measurements of tree-based diameters. The first dataset's values are in units of centimeters, while the second dataset's values are in units of meters. So we calculate the mean absolute deviations using the same procedure that we did before for the two samples. We first calculate the sample means, and once we have those, we then calculate the MAD as being the sum of the absolute value of the deviations divided by the sample size, which in this case is 5, and for both samples, and we end up with an MAD for sample A of 44.68 centimeters and an MAD for sample B of 0.4468 meters. Now notice, there's a few things to notice here. Obviously, you can plain to see that we have a larger value for the MAD A versus the MAD B. At first glance, we can see that's obvious. Another thing to point out too is for the MAD B, we have 4 decimal places, and you can see the use of the space after the third decimal place. So one common practice that we'll use in this course is when you have decimal numbers with more than 3 decimal places, that a space is put after every 3 decimal places. And that's why we see the space in this particular answer. Next, we work out the sample standard deviations. Similarly, we use the same mean values that we calculated before, and then we use the formula for sample standard deviation being the square root of the sums of the squares of the deviations divided by n-1, or 5 - 1, or 4. And so we end up with, for sample A, we get SA equaling 55.77 centimeters. And for SB, we get 0.5577 meters. And we can see too that since these are rounded numbers, you can see that we've also included, notice you'll see that these values have been rounded to 1 more decimal place than the base data. So we have 2 decimal places for sample A compared to 1 decimal place in the base data. And for sample B, because we go to 3 decimal places, you can see that the answer has 4 decimal places. And then we also include, for both samples A and B, in the brackets, you can see that we also keep track of a version of the answer rounded to two further decimal places. And that follows the rule of thumb that we had discussed before. Now we can also calculate what the standard deviations would be if we were considering these to be populations instead of samples. We would simply do the same calculations, except the one difference being that under the square root sign we would divide by n instead of n-1. So we would divide by 5 instead of 4. And so that would give us a sigma A of 49.88 centimeters and a sigma B of 0.4988 meters. The results of these calculations show different values between samples A and B for both MAD and sigma or S. Upon close inspection, it can be seen that the value for sample A is always 100 times the value for sample B for each measure. Now there's a very good reason for this, and that is because these two samples are actually the same sample. They're identical measurements of the same trees, with the only difference being that sample A has these measurements in centimeters, while sample B has the same measurements converted to meters. If we look at the data sets both in increasing order, so if we line them up so their values correspond, this becomes very clear. For example, the smallest value in the data set for sample A is 72.3 centimeters, which if we divide by 100 gives us 0.723 meters. And similarly, the largest value in sample A, which is 203.5 centimeters, corresponds exactly to 2.035 meters. Now, since the data sets are actually based on the same measurements, their overall inherent variation must be equal. After all, both samples consist of measurement of the same quantity, i.e. base diameter, for the very same trees. The reason why sample A's values for MAD and sigma or S are 100 times those for sample B is simply because there's 100 centimeters in 1 meter and vice versa. In order to be able to compare data sets with different units, measures of dispersion that are dimensionless, i.e. unit-free, are required. And this is accomplished by dividing the measure of dispersion, whether it's the MAD or sigma or S, by the mean, i.e. by mu or x bar. The mean absolute relative deviation, or MARD, is calculated as follows. The MARD is equal to the mean absolute deviation, or MAD, divided by the absolute value of the mean. So for a population, that would be divided by the absolute value of mu. And for a sample, the MARD equals the mean absolute deviation, or MAD, divided by the absolute value of x bar. Now there's a few issues that we should discuss here. One is, of course, that, there is an alternative way in each case of calculating the MARD directly. For a population, it would be the same as the sum of the absolute values of the deviations divided by the absolute value of the sum of all the x values. And similarly, for a sample, it would be the sum of the absolute values of the deviations also divided by the absolute value of the sum of the values. And so the alternative method shown in the brackets here is simply a way of showing how you can mathematically calculate this without first calculating the MAD. Now, another issue that should be mentioned is one particular problem with the MARD is that if your population or sample mean happens to equal 0, which could be the case if you have, particularly if you have a data set with negative and positive values, there's always the possibility that you could have a mean of 0. And if that is the case, actually, then you would be dividing by 0 in calculating the MARD, and so the MARD would become undefined in that particular case. Now note that the formula for MARD will give you the same answer whether the data set is a population or a sample. You just see above two equations that are essentially expressing the same idea, but we interchange the symbols mu and x bar depending on whether we consider the data set to be a population or a sample. So there really is just one formula essentially for the MARD. So let's take a look at how the calculation of MARD looks for these two tree measurement samples. For sample A, the MARD would equal, and now for this we're going to use, because it's a little bit more illustrative and it's a little bit more explicitly meaningful to think of the MARD as the MAD divided by the mean. In other words, the formula as shown not in the brackets above versus the equivalent formulas in the brackets. So we're going to use that more explicit version of the MARD formula here, and we'll calculate the MARD as equaling the MAD for the sample divided by the sample mean. And so for sample A, we get 44.68 divided by 141.7, and we get 0.315 as a rounded answer. And the MARD for sample B is 0.4468 divided by 1.417, which, interestingly, also equals or rounds to 0.315. Now, there's a few things we want to talk about that follow from this. Notice that the above results show equal values for the MARD for both samples. And this is actually consistent with the fact that the samples are actually of identical measurements, with the only difference being that different units are used. So remember that sample A is just a conversion of units of sample B and vice versa. Now, another thing to note here is you might be wondering why we've rounded the MARD values to 3 decimal places. The reason for this is that we'll use a rule of thumb throughout this course that dimensionless measures of variation are rounded to the nearest tenth of a percent, and the nearest tenth of a percent means to 3 decimal places. Now we look at the coefficient of variation. As discussed previously, the standard deviation is more commonly used than the MAD for mathematical reasons. Following from this, the MARD is typically overlooked as a dimensionless measure of dispersion of choice in favor of the coefficient of variation, or CV, which is calculated as follows. For a population, the CVP is equal to sigma divided by the absolute value of mu, and analogously for a sample, the CVS is equal to S divided by the absolute value of X bar. And similar to as we discussed with the MARD, there is a mathematical alternative way of calculating the CVP and the CVS, and you can see that they're slightly different because, of course, with population versus sample, when it comes to standard deviations from which the CVs are derived, we divide for the population, we divide by the population size n, whereas with the sample, we divide by n-1 when we're figuring out the variance and the standard deviation. So we actually, unlike with the MARD, which is the same for a population and a sample, the coefficient of variation uses a slightly different formula. And in fact, because S is generally larger than sigma, the CVS is generally going to be slightly larger than the CVP for the same data set. So those alternative formulas, you can see for population is the square root of the population n times the sum of the squares of the deviations divided by the absolute value of the sum of the x values, and whereas for a sample it equals n times the square root of the sum of the squares of the deviations divided by n-1 divided by the absolute value of the sum of the x values. So the denominators are the same in these alternative formulas, but the numerators are slightly different, again, because of the fact that we use n-1 instead of n for calculating the standard deviations. Now, for the 2 tree measurement samples, we then, and again, we'll use here the more explicit version of the CV formulas where we divide the standard deviation by the absolute value of the mean. And also should note here as well, there's the same issue as with the MARDs, that in the event that you have a data set with a mean of 0, your CV would become undefined. So that's one restriction or limitation that we need to be aware of. So looking at these two tree measurement samples, we would calculate, we can calculate two different coefficients of variation. One, if it's a population for each sample, versus what the CV would be if it was a sample. So if these are taken to be populations, we get the CVP of sample A is 49.8841 divided by 141.7. Notice here we use the version where we keep an extra 2 decimal places of accuracy. So 49.8841 divided by 141.7, which rounds to 0.352. And for the second data set B, the CVP would be 0.498841 divided by 1.417, which equals 0.352. And again, notice here we get the same CVP for both data sets A and B. And likewise, for if we treat the data sets as samples, we get CVSA as 55.7722 divided by 141.7, which equals 0.394. And for B, we get 0.557722 divided by 1.417, which also equals 0.394. So once again, we see that the values in each case are equal for both samples, which, as with the MARD calculation, reflects the fact that it's just the same actual data, the same measurements expressed, with the only difference being that different units are used. So when that is the case, we will have identical values for any dimensionless measure of dispersion, whether it's the MARD or the CV, whether it's a population or a sample. Now, a final note about dimensionless measures is that since such measures are based upon dividing a dimension measure of dispersion by the corresponding mean value, it's implied that a lower mean will yield a higher dimensionless measure and vice versa. However, this mathematical fact is only relevant when the data values are measures of something for which 0 means none or equals none of whatever the quantity it is that we're measuring. In other words, where a value further away from 0 means that there's more of the quantity and vice versa. This condition is actually the defining characteristic of ratio data, and it distinguishes ratio data from interval data. Therefore, we can say that dimensionless measures of dispersion, as defined here and illustrated in the previous example, apply only to ratio data. The following is a set of 2 practice questions meant to provide a review of the material covered in this lesson. In question 1, we're given the following set of maximum temperatures in degrees Celsius over a consecutive period of days as follows: -3, -1, 4, 0, -11, -8, -2, 1, -1, -5. And we're asked to calculate the following measures of dispersion if they apply, and where they do not, explain why. Range, mean absolute deviation, variance for both a population and a sample, standard deviation for both population and sample, mean absolute relative deviation, and coefficient of variation for both population and sample. For this question, where there's no distinction between population versus sample, we'll simply use the sample notation. We start here with calculating the range, and the first step we take to do that is we order the data set. Here we put the values into increasing order from a minimum of -11 to a maximum of 4. And for the later calculations, we note here that the size of the data set is 10. Now to calculate the range, we simply take x max minus x min, which equals 4 minus negative 11, or 4 plus 11, which equals 15 degrees Celsius. Next, we calculate the MAD. So we first calculate the mean of the data set, which equals the sum of the values divided by the number of values, which equals minus 26 divided by 10, which equals minus 2.6 degrees Celsius. So to calculate our MAD, we add up all of the absolute values of the deviations and we divide it by the size of the data set, which gives us 33.2 divided by 10, which equals 3.32 degrees Celsius. Next, we calculate the variances. The population variance sigma squared and sample variance s squared are calculated using the formulas discussed previously. So in both cases, the numerators are the same, and instead of taking the absolute values of the deviations, we square the deviations. And then in the case of sigma squared, we divide by the population size of 10, whereas for s squared, we divide by the sample size minus 1, which equals 9. So we get sigma squared equals 174.4 divided by 10, which equals 17.44 degrees Celsius. And s squared equals 174.4 divided by 9, which rounds to 19.4 degrees Celsius. Next, to get the population and sample standard deviations, we take the square roots of the variances that we just calculated, which work out to be, for sigma, it's rounded to 4.2 degrees Celsius, and for s, it's rounded to 4.4 degrees Celsius. Finally, we note here that, as discussed previously in the lesson on types of statistical data, temperatures in degrees Celsius are interval and not ratio data, because 0 degrees Celsius does not mean there's no temperature or no heat energy, but rather 0 degrees Celsius is a reference point, specifically where water melts or freezes at standard pressure. So therefore, neither the MARD nor the CV applies here. In question 2, a consulting firm wishes to hire one of 2 7-person crews to conduct field sampling in a forest. To determine which crew is more consistent, each crew is asked to have all of its members measure the height of the same tree. However, the 2 crews are located in different towns, so the trees they are measuring are different. And as it turns out, one crew's tree is considerably taller than the other. It is therefore decided that the mean absolute relative deviation, the MARD, is to be used, with the lower MARD value signifying a crew that is more consistent in its measurements. Given the crew's measurements below, in meters, determine which crew should be selected. Crew A's measurements are 8.2, 9.9, 10.1, 8.1, 9.8, 8.5, 9.2, and crew B's measurements are 31.4, 30.7, 28.6, 29.1, 32.0, 30.2, 28.9. For each crew, the MARD is calculated as per the procedure followed in the previous example. First, we calculate the sample mean, and if the sample mean needs to be rounded, then because we're using this number in the subsequent calculation of the MARD, we would round the answer to 2 extra decimal places. That turns out to be the case for both crew A and crew B here. So the sample mean for crew A works out to 9.1143 meters, and the sample mean for crew B works out to be 30.1286 meters. So then when we calculate the MARD, we, in both cases, take the sum of the absolute values of the deviations and divide by the sample mean just calculated. So we end up getting, for crew A, the MARD works out to be rounded to 0.080, and for crew B, the MARD rounds to 0.036. And then we note here that the MARD for crew B is smaller than the MARD for crew A. Therefore, we conclude that crew B should be selected. Now note, it can be shown that the MAD for crew B is approximately 1.1, which is actually greater than the MAD for crew A, which is approximately 0.73. The reason why crew B's measurements have less relative dispersion has nothing to do with different measurement units. As in this example, both crews' measurements are in the same units of meters. Rather, this result is due to the fact that crew B's data values are bigger because they measured a taller tree than did crew A. I hope that you found this video helpful. If you liked it and would like to see more from Ursa Campus, then please subscribe. And also, if you'd like to send your feedback, that's always welcome too. Thanks for watching, and I wish you well with your studies.